Alrighty, welcome back everyone. So we are going to continue our journey into area approximations today. But before we do that, let's knock out the homework that we had, and I think that homework was from 4.2. Yeah, 4.2. Alrighty, we start with number 5, and it was start, so we'll definitely go over it. We had the summation I from 1 to 6 of 3i plus 2. Now you don't need this in parentheses, it's just being extremely thorough, so no big deal. But let's see, what would that be? Well, that would be, we're going to start out, I is going to start with 1, and so we're going to get 3 times 1 plus 2 plus, and then we're going to have, it's going to increment, so it'll become 2, so 3 times 2 plus 2 plus 3 times 3 plus 2 plus 3 times 4 plus 2 plus 3 times 5 plus 2 plus 3 times 6 plus 2. Alrighty, so what will that give me? 3 times 1 is 3 plus 2 is 5 plus 8 plus 11 plus 14 plus 17 plus 20. So let's see, that's 13 plus 11 is 24, 38, 55, 75 is what I get. Well, there was actually an easier way of doing that, right? 5 plus 20, 8 plus 17, 11 plus 14. Each of these adds up to 25. How many pairs are there? 3. 3 times 25, 75. Oh, you gotta love that. Once you see Gauss's little technique, it never goes away, which I guess is a good thing. So let's see. Next one was number 7. And this is just, more annoying than anything. We had summation k equals 0 to 4 of 1 over k squared plus 1. Alrighty, we're going to have a lot of fractions, so here we go. It's going to start at 0 and then increment all the way up to 4. So we're going to have 1 over 0 squared plus 1 plus 1 over 1 squared plus 1 plus 1 over 2 squared plus 1 plus 1 over 3 squared plus 1, and finally plus 1 over 4 squared plus 1. Well, this is going to give me 1 over 1 plus 1 over 2 plus 1 over 5 plus 1 over 10 plus 1 over 17. Ugh, fractions. I'm okay if you leave it just like this, but if you want to do it all the way out, the common denominator is going to be 2, 5, 10, 170, 17's prime, so 17 and the 10 take care of all of them. So this is going to be 170 over 170 plus 85 over 170 plus, oh gosh, 34, 17 plus 10. Oh, man, I don't want to do that in my head. Let's see. I'm going to add this way and then add it to 170. So 27, 61, 146. So 170 plus 100 and say 146. Is that right? 316. So this equals 316 over 170. And I'm totally cool with leaving it just like that. So I don't want to do that anymore. So that was number 7. I'm going to clear this. Alrighty, so now for the fun ones. 17 starts off really nice. 17 is summation I equals 1 to 12 of 7. Well, what does that mean? Well, it means it's going to be 7 plus 7 plus 7 plus ... a total of 12 times. But the easiest way to do that is just 7 times the n, which is 84. That's what you're going to get if you add it all in by hand. That's just to illustrate that little property that if you have a summation of a constant, it's just the constant times your n. That's your value. Alrighty, and so the next one was 20. And let's see, we have summation I from 1 to 16. 1 to 16. And this is going to be 5i minus 4. 5i minus 4. Now, the reason that they picked 16 for the summation is so you wouldn't be tempted to write this out 16 times and then add everything together. Instead, let's use the properties of summation. So I can rewrite this as a sum. So this is going to be I from 1 to 16 of 5i minus I from 1 to 16 of 4. And now the next thing I can do is I can take that 5 out, right? You can cross a constant across the summation. This is 5i 1 to 16 of I minus I from 1 to 16 of 4. Okay, well, I've got 5, this is going to be 5 times, well, when I do the summation of I, 1 to n of I, that's n times n plus 1 over 2, right? That's what that formula was. So my n is 16, so this is going to be 16 times 17 over 2. Okay? Minus, well, this is just 4 times 16, 64. Alrighty, so let's see, that's 2, that'll go in that 8. 8 times 5 is 40, times 17 is 680, minus 64, I think that's right, 616 should be your answer. So hopefully I did that right. If I didn't, my heart was pure. I gave it my best shot. My math skills may be a little weak. Alrighty, so let me clear that. I'm not using a calculator. I'm doing all this in my head, so mistakes can definitely happen. Alrighty, 21. So 21 we have, oh, this is a fun one. Summation from 1 to 20. Again, not something you want to write out term by term of I minus 1 quantity squared. Alrighty, we do not have an expression that can handle this. So the only way that you can work this problem with what we have so far is to expand this out. If I square this, I get summation I from 1 to 20 of I squared minus 2i plus 1. And now I can break it into its terms. Summation I from 1 to 20 of I squared minus 2 times summation I from 1 to 20 of I plus summation I from 1 to 20 of 1. Alrighty, so now I can do this. This is the formula that I don't keep in my brain at all times, but I'll look back over it. So the summation from 1 to n of I squared was equal to n times n plus 1 times 2n plus 1 over 6, right? So in that case, this is going to wind up being, my n is 20, so I'm going to get 20 times 21 times 41 over 6 minus 2 times, now summation of I, which we just did, so that's n, my goodness, if I had good sense, that'd be dangerous. N is 20, so that is 20 times 21 over 2, and then plus 1 times 20, 20. Alrighty, so now I can work with this. So become a 3. If I make that a 10, the 3 will go into 21 7 times. So I'm going to get 70 times 41. Oh gosh. 70 times 41. 2870? I think that's right. 2870 minus 2, cancel that 2. 21 times 20 is, what is that, 420? Plus 20 is, let's see, so 20 and the negative 420 are going to become 400. If I subtract 400 from that, I wind up with 2,470 for my final total. Whew. Alrighty, that was a lot of work to get there, but it beats the heck out of adding 20 of these terms together. Can you imagine how many mistakes you would get? It would just be ridiculous. So, and last but not least, what did we have? 25, is it? So 25, we have the limit. And this one I ask you to just do the limit as n goes to infinity. Don't worry about approaching it by doing n equals 10, 100, 1,000, all that. Just go straight to infinity. Way easier that way. Of the summation I equals 1 to n of 2i plus 1 over n squared. Now, it starts off looking just terrible, but it's not. The n is a constant, right? Whatever this is, it's a constant. Even if I think of it as infinity, I've never actually, infinity isn't a constant, but I'm not touching actual infinity. I'm getting really close to it. So whatever value I settle on, that is a constant. So I can move it across the summation. So I can rewrite this as 1 over n squared times, oops, let me backtrack. Almost forgot my limit. Limit as n goes to infinity of 1 over n squared times summation I equals 1 to n of 2i plus 1. Okay, so now I'm going to rewrite this as the limit as n goes to infinity of 1 over n squared times, big bracket, 2 times summation I equals 1 to n of I plus summation I equals 1 to n of 1. Okay? And I know what that formula is. I know how to figure out that. So this is going to be the limit as n goes to infinity of 1 over n squared times, well, let's see, this is going to be 2 times n plus 1 over 2 plus, because that's what the summation of I is, it's n times n plus 1 over 2, and then multiplied by the 2 that I have in front. And then this is just a summation of a constant, so 1 times n. Okay? So now I can multiply all this together, get a common denominator, and see what I get. So this is the limit as n goes to infinity of, I've got 1 over n squared times, well, this is going to be 2n times, oh wait, easier, 2's cancel. N times n squared is n. So this is n squared plus n is plus 2n. Okay, so that's going to be the limit as n goes to infinity of, well, n squared over n squared plus 2n over n squared. Whew, we're almost there. That's going to be the limit as n goes to infinity of, that's a 1. This becomes 2 over n. If I now apply the limit, this term goes to 0, and I'm left with 1. That is my answer. That is the actual limit as n goes to infinity of this summation. So there you have it. that is all the homework. So hopefully this went well, and we can jump on back into area approximations. So let me clear the screen and let's get going. Clear screen. My goodness, clear screen. I think my delete key is going out on my computer. Alrighty, so let's see what we have. Okay, so we're going to start off with kind of a strange thing that's just kind of falling out of left field. Let's say that I have a function, and I'm able to draw a nice straight line. I've only done this 1,000 times. Let's say I have f of x equals x squared. Now I want to do something really, really strange. I want to know, assuming that I can draw that, I want to know what the area is underneath the curve y equals x squared, f of x is x squared, from 0 to 4. I want to know what all this area is underneath there. Okay? Now, how do I figure that out? Any ideas? Well, you haven't seen it before. It's not really fair to ask you. I'm going to do something that's going to seem like it's not a very good idea. It turns out to be perfectly fine. I'm going to take that function, and this is not drawn to scale. It gets way steeper than this by the time the x equals 4. Okay? So I am going to divide this into 4 intervals. Isn't that nice? And I'm going to draw rectangles. So I can figure out what the area of a rectangle is. Okay? Now I'm going to call this R1, R2, R3, and R4. So if I can find the area for all of these rectangles, right? Not too bad. If I do that, I have an estimate for the area that's actually under the curve. Will that estimate overshoot or undershoot the actual value? Well, in this case, it's going to overshoot because I have all this stuff that's on top. And this stuff should not be added, but it is because we're dealing with rectangles, right? So I'm going to overestimate about all of this stuff, but that's okay. Alrighty? So in order to get the height of the area of a rectangle, okay, area is just, in this case, the width times the height. Okay? Now, what is the width of each of these rectangles? Okay? The width is equal to, well, I can just look at it and tell you the width is 1, but let's say I couldn't look at it and tell you it was 1. Well, I'm going from 0 to 4, and I have 4 rectangles that are all the same width. How do I figure out what that width is? Well, 4 minus 0, the total width, divided by the number of rectangles. And if I wanted to do that in more general terms, b minus a over n, where b is your endpoint, so this right here is b, and a is your starting point, and then n is the number of rectangles. Not bad. Not bad at all. Okay? So, let's actually do this up with a nice table. So if you will allow, I'll give you a second to copy it down. Think about it. Main thing is that each of the widths is going to be 1. And I could have found that by using the last x value minus the initial x value over the interval divided by the number of rectangles. Just want to say all that. Now, what I'm going to do is I'm going to erase all the stuff right here, and I'm going to make a table for the area of all these rectangles. I don't want to redraw it if you're wondering why I'm erasing rather than redrawing it. So here we go. Well, let's see. I'm going to have the width and the height. If I could spell H-E-I-G-H-T. There we go. Alrighty. In the area. Alrighty. So R1, R2, R3, and R4. Okay? So, the width, 1. What is the height of R1? Well, I know that my function is f of x equals x squared. So, what is this y value? This y value is I get this y value when I plug in this x value into the function, right? So this y value is f of 1, which is 1 squared, which is 1. So I'm going to get 1 squared, which is 1. Okay, what about the height of the second rectangle? Well, it's the height when I look at plugging a 2 into my function. So right here, this is f of 2, which is 2 squared, which is a height of 4. So, oh, I forgot to do this part. 1 times 1 is 1. Right, with the 1, the height for the second one we said was 2 squared, which is 4, which means the area is going to be 1 times 4 is 4. Now the area of rectangle 3, well, that height is what I get when I plug in the x value 3 into the function. So f of 3 is 3 squared, which is 9. So 3 squared equals 9. 1 times 9, 9. Alrighty. Last but not least, this one right here, which kind of off the chart, but I would get this value by plugging in x equals 4. So I would have f of 4, which is 4 squared, which is 16. That's that y value. So 4 squared, 16. 1 times 16 is 16. Alright, so now we can add all these together. I get 1 plus 9 is 10, 4 plus 16 is 20, 10 plus 20 is 30. Okay? Now, we already said that this is an overestimate because I'm including all of this extraneous stuff on the top of the rectangles, right? So, that's okay. But just want to make sure this is not the actual area under the curve. This is an overestimate of the area under the curve. Okay. Now, what I want to do is take the process that we just did and rewrite it in sigma notation. So I'm going to clear the screen and let's go to sigmas. Okay. I may have to redraw the graph. That's okay. So the area is equal to summation I equals 1 to how many rectangles do we have? 4. And really it's R sub I, right? Because it's rectangle 1's area plus, oh, you know what, I should do AR1 there. AR1 plus AR2 plus AR3 plus AR4, right? The area of the rectangles. That's how I would find that. So how would I set this up? Generalize it a little bit. So it's I from 1 to 4 of, we're going to have the width of the I rectangle times the height of the ith rectangle, right? That would give me the area of each of the rectangles. Alrighty, well, I equals 1, 2, 4 of, what is the width of each of these rectangles? Well, that is b minus a over n times the height, which I'm going to put a question mark there for right now, okay? And so I'm going to rewrite this expression as I equals 1 to 4 of, well, b is 4, a is 0, 4 minus 0 is 4, divided by 4, 1, times, now I need to tackle this height thing, okay? I'm going to do a little bit of scratch work right over here and see if I can figure out the pattern, okay? For R1, the height was f of 1, right? For R2, the height was f of 2. For R3, the height was f of 3. And finally, R4, the height was what? F of 4. Alrighty. So what is the pattern? Well, for each of the rectangles, I feed in that value into my function, and that will give me the height. So how do I write that over here? Well, this is f of I. Would you agree? So when it starts at 1, I'm going to get f of 1. Well, what is my f? Well, let me put that right here. My f of x is x squared. So I could rewrite this finally as I equals 1 to 4 of 1 times, well, my function is x squared, so f of I is just going to be I squared. Alrighty? Well, I can do that, right? Because that is the summation, I already have that summation, don't I? I don't have to do this. So the summation of I squared is going to be, if you remember, it was, do the scratch work right here, I squared was n plus 1, 2n plus 1, all of that over 6, right? So what's my n? N is 4, so it's going to be 4 times n plus 1, 4 plus 1, times 2n plus 1, so 8 plus 1 over 6. Well, that's going to be 4 times 5 times 9 over 6. Okay, so I'm going to, let's see, that'll become a 2, that'll become a 3. 2 times 3 is 6 times 5, 30. What do we get when we did it manually? 30. Exactly right. So this is the very first example of using sigma notation to solve a real problem. Okay? Now, let's take a second to digest this. Okay. And now let's move on. Let me clear the screen and we'll go to the next piece. Here we go. Okay, so let me redraw the function again. Okay, again, this isn't drawn to scale because it goes up way faster than the way I've drawn it. But that's okay. Let's see, let's say that's 4, 2, 3, and 1. Okay, now, what we did, I shouldn't say just me, we all did it. We just found an estimate for the area, right? And we had those giant rectangles that kind of stood up, and they were okay. what if we wanted to get a better estimate for the curve? What could we do? Well, one thing we could do is make more rectangles. Okay, so what if I make, this is x squared, what if I make n equal to 8 instead? Okay, and I'm going to put a few more values in. Alrighty, so not too bad, and this is a 3/2. Hard to read that 3. Okay, so here I go. Going up, using the right side, the right endpoint, if you will, and drawing rectangles. Ooh, that's a lot of drawing. I think I just went off the edge. We'll just put that rectangle right there. Alrighty. Hopefully y'all can see that. I'll even lower it down a little bit to make sure you can see it. Okay. So here's the question. Will that be a better estimate than n equals 4? Yes. A much better estimate. Why? Well, the extra area that it's accumulating by going above the actual curve is nowhere near as much as it was when n equals 4. And you can imagine, I'll do this super fast. I do n equals 1. That is an absolute hideous estimate because this area here will actually outdo this area. So it's definitely better to increase our n, okay? So if n is 8, we need to set up a table and do a bunch of little things. So here we go. We'll make a table again. I'm going to have my width, my height, and my area. Alrighty. Now this is not going to immediately be as easy as the first one was. So, alrighty. So I've got R1, R2, R3. That's a 3, I promise. R4, R5, R6, R7, and R8. Alrighty. So, what is the width of each of these rectangles? Well, the width is just b minus a over n, so it's going to be 4 minus 0 over 8, because now I have 8 rectangles. So that's going to be 1/2, right? Alright, so I've got 1/2 for my width. Now, what is the height? Well, the height of this is what I get when I plug in f of 1/2 in, right? Well, f of 1/2 is just 1/2 squared. Alrighty. 1/2 squared is going to be 1/4. 1/2 times 1/4. I'll even do that over here, like so. And that equals 1/8. Okay? R2. Now, what am I feeding in for R2 to get the height of this rectangle? Well, I'm feeding it in 1. So, f of, and if you allow me, I'm going to write 1 as 2/2 for absolutely no reason. This is going to be 2/2 squared. So this is going to be 1/2 times 4/4, which equals 4 over 8. Oh, this is hard to write. I should have made this bigger. Alrighty, hopefully you can read it. So now, again, the width is 1/2. What do I feed in for R3? Well, R3, I'm going to feed in 3/2. So this is f of 3/2, which is 3/2 squared. So that's going to be 1/2 times, what is 3/2 squared? Well, that's 9/4, which is just going to be 9/8. Okay, 1/2. I'm going to feed in 4/4, right? So 4/4, 4/2. That's going to be 4/2 squared. So it's going to be 1/2 times 4/2 squared is 16/4, which is what? 1 time, so it's 16 over 8. Alrighty, 4 to go. 1/2. What do I feed in to find the height of the 5th rectangle? Right, I feed in 5/2, which is going to give me 5/2 squared. Oops. So 5/2 squared. So over here it's going to be 1/2 times 5/2 squared is 25 over 4, which is 25 over 8. 1/2. I feed in 6/2. That's 6/2 squared. 1/2 times 36/4. Ooh, that's hard to say, sorry. So it's going to be 36 over 8. 1/2 f of 7/2, and that's going to be 7/2 squared, which is going to be 1/2 times 49/4. So 1/2 times 49/4 is going to be 49 over 8. And last but not least, 1/2. What do I feed in? I feed in 8/2. It's going to be 8/2 squared. So this is going to be 1/2 times 64/4, which is 64 over 8. Whew, that's a lot of work. So let's see. If I do all these together, I'm going to get 1/8 plus 4/8. I'm just going to eliminate the 8s, just add the tops. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55, plus 36 is 91, plus 41 is 140, plus 64 is 204 over 8. Does that look right? Let me go through that math again. It's, let's see, 1, 2, it seems, does that seem right? 20, 160, 30. You know, yeah, I think I'd go for that. I just did it again. 14 plus 16 is 30. 55 plus 31 is 91. 49, 140. Plus 64 is 204 over 8. Yeah, I agree with that. I think that's correct. Now, why on earth did I go through all this? Well, I went over this excruciating process so that I could come up with another sigma notation. So in this case, I'm going to do I from 1 to, now it's 8. And what do I put over here? Well, I've got my width, which is 1/2 times f of, what was I feeding in? Well, I was feeding in 1/2 for R1, 2/2 for R2, 3/2 for R3, 4/2 for R4, dot, 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 all the way to 8/2 for R equals 8. So I'm feeding in the I, whatever that is, over 2. Okay? Would you agree? 1/2, 2/2, 3/2, 4/2, 5/2, etc., all the way down. Okay? So what does that give me? Well, let's see, this is going to be, the function is x squared, so now I can rewrite this as summation I equals 1 to 8 of 1/2 times, well, this is I squared over 4, because that's what happens when I feed I over 2 into x squared. F of I over 2 is going to be I squared over 4, right? If I just square it, it's this thing squared. Okay, so now that I've got that, I get this right here. So this is going to equal summation I from 1 to 8 of, let's see, I can do, this is 1 over 8 I squared, which is going to be 1 over 8 summation I equals 1 to 8 of I squared. Okay, but now I know the formula for that, so this becomes 1/8 times n, which is 8, 8 times n plus 1, 9, times 2n plus 1, 17 over 6. Okay, so what do I wind up with? Well, gosh, wow, that's not going to be fun. All right, that's okay. The 8's cancel. The 3 cancels here. And I wind up with, what is that? 51 over 2, which if I multiply by 4 over 4, I get 204 over 8. The exact same thing we had up here. Which one would have been easier to do? Making all this chart, adding all the fractions, or using the sigma notation? Yeah, by a mile, sigma notation. Alrighty, I'm going to clear the board. I think I can clear the board here. No, I'm not going to clear the board, I'm going to erase. Let me erase. So yeah, make sure you get all this down. And I'm just going to erase this bottom part, okay? Alright, so let me erase this right here. Yeah, I'll erase from this over. I can make my eraser a little bit bigger. Alrighty, almost done. Erase, 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 erase it. Alrighty, now, here is the $100 question. What is a general way to write this? Look, all I want to do is I want to write this for a general n. I don't want n equals 4, n equals 8, I just want n. So how do I do that? Okay, well, it would be the summation I from 1 to n of b minus a over n. Okay, that's how I got my width each time. How did I get this though? I went from f of I to f of I divided by 2. Where did that I over 2 come from? The I over 2 comes from because the width of each one of these pieces is b minus a over n. That's what's getting multiplied by the I. So this is really f of b minus a over n I. If this width is a half, it becomes I over 2. If this width is a 1, it just becomes I. If I divided it into 13 pieces, it would be I over 13. That makes sense? Excellent. So this right here is important. This is the general formula for approximating area under a curve using the right endpoint. Okay? Another way to say that is this is the right endpoint formula. Right endpoint. Okay? What do I mean when I say right endpoint? Every one of these rectangles uses the right-hand side to draw the height of the rectangle. Right? Every one of these is using the right side of the rectangle. So that we call that the right endpoint. This is the right endpoint formula then. Okay? So let me clear the screen. Let's go to the next one. Let's do some work with it. So here we go. A lot of work to clear. So the right endpoint formula, we have the area is approximately summation I from 1 to n of b minus a over n times f of b minus a over n times I. Okay? It looks really weird, but that's when we did all the work previously, so this didn't just fall out of the sky on you. This is in the case of for f of x equals x squared. Let's do n equals 4. We'll have summation I from 1 to 4 of 4 minus 0. And this is n equals 4. I need to actually give you 0 to 4. That's the interval. So 4 minus 0 over 4 times, we're going to have f of 4 minus 0 over 4 times I. Okay, and in our case, the function is x squared, so this becomes I equals 1 to 4 of 1 times, it's just going to be 1I, and when I run f of I get I squared. And we've done this, and it works out to be whatever that other one, whatever that summation was. And then for f of x equals x squared on 0 to 4 with n equal 8, we get summation I from 1 to 8 of, well now it's 4 minus 0 over 8 times f of 4 minus 0 over 8 I. Okay, so what did that wind up being? This wound up being summation I from 1 to 8 of 1/2 times f of 1/2 I, which is I over 2 squared. And we just did that one, and we'll wind up with the answer, okay? So now, let's take exactly what we have. I'm going to erase. I'm going to be very generous with my erasing though and leave the formula upstairs because I want to do something with it. Alright, so here we go. Erase this with a much bigger eraser. I don't have to be quite as careful. Alrighty, so what about for f of x equals x squared between 0 and 4, n equals, you ready? Infinity. What happens? Well, we saw that when we went from n equals 4 to n equals 8, our approximation looked like it would be better because there was less area above the curve. If I keep increasing the number of rectangles all the way to the limit as n goes to infinity, what happens? Now I can write this as the area does not approximate the area equals the limit as n goes to infinity for summation I from 1 to n of b minus a over n times f of b minus a over n times I. And in our case, we have x squared, so this is going to be summation I. Actually, let me make the summation not quite so large. So this is going to be the limit, I'll start right here, as n goes to infinity of, let's see, we've got summation I equals 1 to n of, b minus a is what? Well, we've got 0 to 4, right? So this is going to be 4 over n times 4 over ni fed into my function is going to be 4 over n squared. So 16 over n squared I squared. Does everybody see where that came from? This was 4 over n. b minus a is 4. 4 over n times I squared. I get 4 times 4 is 16. N times n is n squared. And I times I is I squared. So I get this expression right here. Okay? So this is going to be the limit as n goes to infinity of summation I from 1 to n of 4 over n times, well, this is going to be, really, there's not a lot. I should just do it out, shouldn't I? Let me erase that. Where's no, I can actually save a step here. This is going to be 4 times 16, 64 over n cubed times I squared. N times n squared, n cubed, 4 times 16, 64. Now I can, this is a constant, I can move it across the summation so it becomes the limit as n goes to infinity of, I'm going to have 64 over n cubed times the summation I from 1 to n of I squared. But we know that, so this becomes the limit as n goes to infinity of, well, this becomes, well, 64 over an n cubed, 44, forget that, n cubed times, well, this is n times n plus 1 times 2n plus 1 over what? 6. Okay? Ooh, I need more room. So, this is going to be, let's see, would y'all be okay if I erase some of the top stuff up top so I can put that in? Alright, let me erase that just a little bit. I am running out of room. I need about that much more space. Okay. We're heading up to the top. Alrighty, so this becomes the limit as n goes to infinity of 64 over n cubed times, well, what is this? This is n squared plus n times 2n plus 1, and all of that over 6. Okay, so this is the limit as n goes to infinity of 64 over n cubed times, here we go, n squared times 2n is 2n cubed. N squared times 1 is n squared, plus 2n squared is plus 3n squared, plus n, all of that over 6. Okay, so now if I divide that by 2, I get a 3 on the bottom and a 32 on top. So this is the limit as n goes to infinity of, let's see, 32 over 3 times, let's see, I'm going to get 2n cubed over n cubed, which is going to be a 2 plus 3n squared over n cubed, 3 over n plus n over n cubed, 1 over n squared, and now I apply the limit. 0, 0, 2 times 32 over 3, 64 over 3. That is the actual area underneath the curve f of x is x squared between 0 and 4. This is the real area. This isn't an approximation anymore. This is exact because we've just added up an infinite number of rectangles. What did we get? 64 thirds. We're going to do a lot more of this over the next lecture and a half. So buckle up. You're going to see this more and more often. This is where we're heading for the next couple of lectures, is looking at an infinite number of rectangles added together gives you the actual area underneath a curve. Okay? And in this case, that answer is 64 thirds. So we went from a not so good estimate of 30, which would have been what, 90 over 3, to what was the last one? I don't even remember what the last one was, but it was like 24 or so approximately. I wish I could remember what that was, but it's been erased and I don't have it written down. And then we get to this one. This is the real area. Okay? So let me clear this and give you a couple of homework problems so you can work on. So here we go. Clear this. Okay, so for your homework, again, this is going to be from 4.2. Tackle number 19, but with special instructions. Number 19. Alrighty, number 19 has f of x is equal to 2x plus 5. If the interval that wants you to get the area under the curve is 0 to 2, and it wants 4 rectangles. Alrighty, so here are your instructions for the homework. So part A, calculate the estimated area by hand. In other words, don't use a formula. Literally draw the curve, make rectangles, do 4 rectangles, add up the area of each one of the rectangles and get an estimate, okay? And that's for n equals 4. Part B, use the right endpoint formula that we went over. For n equals 4, n equals 8, and the limit as n approaches infinity. Okay? So, for the right endpoint formula, take extra care that when you get to f of b minus a over n I, you're not going to wind up with this stuff squared. You won't get b minus a over n I squared, because my function is not f of x equals x squared anymore. So you're not going to use this. Instead, your function is going to be 2 times b minus a over n plus 5. That, hold on, from I, b minus a over n I times 2 plus 5. This is your actual height. So that's what you're going to use for that. And then, of course, it's going to vary. N is 4, N is 8, and you'll leave it as a generic N, and then do it all the way out. So, alrighty. Good luck with homework, especially this right endpoint. Just try. Give it your best shot. And then I will see you next lecture. Take care, stay safe, and bye-bye.